start with whatever. Yes, sorry, what I didn't show you. So we have a label in the program, and we have this A, which is an abstract element. So it's going to be an element of our abstract domain that we will define later. So we will have this abstract state. We will pass it through the whatever abstract semantics of the first statement, and then we'll through the abstract semantics of the second statement. For assignments, we will go through an operation that will take care of the assignment for us. This is a specific operation that will be done in the abstract domain. For if then else, it's very similar. So we just take the expression. So there is going to be a special operation that does the filter. Essentially, we take our abstract domain element and we will modify it to satisfy the expression, either the expression or its negation. We will go through the two paths. Essentially, first either the false branch or the true branch, and then we will merge the results. This is the join operation in the abstract domain. And for while loops, we do essentially as the if. We have to do the filters and the join, but we have to do this in a fixed point kind of loop. So starting from the bottom element of our abstraction, we're going to do this fixed point iteration, and it's going to be an abstract fixed point iteration because we need to enforce termination in our analysis. And so we will use an operation that is called widening to enforce, basically jump to a post-fixed point and terminate there. I'll give you examples in a second, will make more sense. But once we have that, we can do the verification, the sound verification of the properties. In particular for state properties, the sound verification is like this. So essentially, whenever we're going to do this over approximation of the states, we can check if this over approximation satisfies the property, and if so, then since it's an over approximation, we know also that the original, the set of actually reachable states satisfies the property. It doesn't work the other way around, so it could be that our over approximation is actually on the other side, and then we don't know if the property is true. Okay, in a few minutes I'll show you some abstract domains. Starting from the simple ones. So we're going to look at some non-relational domains. So these are domains that basically give you abstractions of the values of single variables, not relating them to each other. And then this one is an example of a relational domain, we call it. So we keep also relationship between variables in a program. So let's do the science. So here, instead of collecting concrete values of the variables, we replace them with the sign values of the variables. You will get an example in a second. I know it's a bit abstract. So the idea is our abstract domain is going to be a map from variables to the sign of these variables. Okay, so the sign is going to be one of these. So positive, 0, negative, or positive or 0, different from 0, and so on. So the operations that we need for our abstraction are the order, list upper bound, greatest lower bound. These are all defined by this class diagram. The assignment operation, basically you take whatever expression, you evaluate it according to the sign rules. Sign rules are like this. So positive plus positive gives you a positive value, or negative plus negative gives you a negative value, and so on. And then the filter, what it does, it modifies the expression to satisfy the guard of the operation. I'll show you the example in a second. We don't need any widening here because this is a finite lattice, so we don't have any need to enforce termination essentially. So, show you an example so it makes more sense. So this is our program from before. This is the property that we want to prove. So we want to show that basically any state that we reach in our program will always have R strictly greater than 0. No, greater or equal than 0, sorry. So I start here there's nothing, I mean, it doesn't matter. We fix the values at A, B, so these are, their sign is greater or equal to 0, so it's positive or equal to 0. At the next step, we assign 0 to Q, so Q if the sign of Q is 0, and we continue to point 5, where R is positive or equal to 0. At 6, it's the same, nothing has happened, we just went from 5 to 6. Now we have the guard. The guard is checking whether R is greater or equal to B. And so it's not modifying our sign. And now this is where things change, because now we have R minus B. So we have to do the operation in the sign domain. So we have something positive minus something positive. And here we don't know the sign of this anymore. It could be negative, it could be positive. So we end up with top. For Q, we get from 0 to something strictly greater than 0. And then we have to keep doing the iterations. We have to reach a fixed point in the abstract. So here, we go back to 6. So at 6, we have to basically take 5, join whatever we get from here. So this one was 0 before, it's strictly greater than 0 after. When we merge them, we get the least upper bound. And this one is greater or equal to 0, so positive or 0. And this one remains top, and so on. We continue. This one, we do the guard. This one will say that it's greater or equal to B, so we will get again that this is greater or equal to 0. We lose it again because of the operation, and so on. This is strictly greater. We go back. Now we have found the same element as before, so this is our abstract fixed point. We are done with the analysis. We can move to point 10, and we are finishing. Now the property that we wanted was that R was always greater or equal than 0. Here we cannot prove it. It is true, but this abstraction doesn't allow to prove it. So we have what we call a false alarm. So what do we do? Okay, I have 2 more minutes. What we do in abstract interpretation is we can use a more precise domain, a more precise instruction. This requires basically doing a bit more effort in the abstraction in exchange for a bit more precision. So for instance here, instead of rounding up to by 10, to the next, I don't know how it's called, well, whatever. We can round up by 5, so 24, 95, instead of becoming 30, it's 25, and so on. If we do that, we actually get to 80, and then we can prove the property. So you see, we have to do a bit more effort, because now we have to add the 5 instead of just tens, but we have more precision. So this is essentially what the interval domain is doing. Instead of just collecting the sign of the variables, we now collect the range of the possible values for a variable. So these are the possible, this is the not complete. I mean, it's a depiction of the lattice. So you have a list element, you have a largest element, the top element, which is the infinite list, the lower and upper bounds, and anything in between. So the operations, the orders are the same as before. For the assignment, you do similarly as for the signs, but now we evaluate the expression with the integral arithmetic. The filter also modifies the expression to satisfy the bounds. If you say greater or equal than 0, you're going to remove anything that is any lower bound that is smaller than 0. But now we have a lattice that is actually infinite in height. So we need what we call a widening. So we need, whenever we have something that is unstable in the bounds, we need to basically do sort of a jump. And what the widening does is to loosen the unstable bounds. So here, for instance, let's say we have an interval 0, 1. At the next iteration, we get an interval 0, 2. This upper bound is unstable, so this one will become infinity. And vice versa here, this is the lower bound, from 0 goes to -1. It's unstable, it goes to -infinity. I'll just conclude with the example and then I'll let you take a break. In the same example as before, the ranges at the beginning, you see these are just the ranges where we can pick the values. Here, the range is 0, 0. This is 0 plus infinity. Here also same, nothing changes. What changes is here. It's a sad story because we are not proving the property yet, but in this case, again, we have 0 plus infinity minus 0 plus infinity. Unfortunately, this gives us minus infinity plus infinity. For Q here, we get from 0, 0 to 1, 1. When we do the merge at the loop head, we get 0, 1 then. And you see at the, want to go here, at the next iteration, the end of the iteration of the loop, we get 1, 2. When we have to do the merge, we will get the interval 0, 2, so we will have 0, 1, 0, 2. We need to do the widening. This will give us 0, infinity. And then if we continue, this is the fixed point for this loop here, and this is the end of the analysis. And here we still have a false alarm. So actually, in this particular case, we actually need the relational domains. But yeah, we ran out of time for today. So we'll continue tomorrow with this part. And yeah, if you have questions, you can come and see me or write in Slack.